Okay. Good evening. You're a very well-behaved crowd. Or cold, I don't know. I was thinking about what to do for this beginner session because I forgot to line somebody else up to do it. And I was thinking that one that I hadn't done in a while was just a very basic. It doesn't like that sound of the room.
Getting feedback, right?
Yeah. I'm getting the best kind of feedback. One topic I haven't covered in a while is just a really basic how to find stuff in the sky. So if you've heard this kind of thing a lot before, I'm sorry. But I think this is really good for the new people. But if you have heard this kind of stuff for a while, I think it's good to, or if you have heard this stuff quite a bit over the years, I think it's good to just kind of reset yourself a little bit and just think about it. Right? So, if you're new to this, my usual, go ahead, do you want to have a seat? Oh, okay, cool. So, if you're starting out, I mean, I think the most common question that I ever get about astronomy is, you know, if I'm starting out, what kind of telescope should I buy? And you know, the answer I try to give is none. Get out under the night sky and use your eyes, right? The second answer that I give that nobody listens to is a pair of binoculars. I really mean it. Like, you know, these are great options. And then I usually just fall back to the 8-inch from Sony and say, just go buy one of those and you'll have fun. And they tend to. But I think getting out and actually learning the sky by yourself with your eyeballs, you will learn to appreciate this hobby a lot better. So I'm hoping that what you take away from this is a little bit of that. So the fun thing about getting out into a deep, dark sky, it's actually beautiful out there right now. I don't know why you aren't all out there observing, but can't imagine. But if you get out into a deep, dark sky, and you know, even if you know the constellations, there is a very good chance that you're going to be kind of washed out, right? So, experienced people will probably recognize this, but even the ones that are experienced may initially be having a hard time picking some things up here. You know, the common things to do are to try and find the bright stars. But the problem that you'll find, and it doesn't translate perfectly in an image, but in a really deep dark sky, you will find that you are completely flooded. It's really hard to. There are so many bright stars out there, and even the dimmer ones, that the difference between them is kind of hard to tell because you're almost kind of going through a little bit of sensory overload. But you know, the usual strategy is to try and pick out the bright ones. Right? I mean, the other trick to this is you guys don't know what field of view this is either. But, you know, so you try to pick out the bright stars, and you'll also kind of notice there's a little bit of this kind of like milky stuff, right? Right? And that's the Milky Way, right? Cutting through the sky. And you'll start to notice that there are some recognizable patterns here, right? So you've already found, so without really knowing what you're looking at, you've already found a couple of markers. So, and then the trick to that is, well, okay, now we need to figure out what are those markers? What am I actually looking at here? And the classic way to learn the night sky is via learning what the constellations are, right? There's a lot of constellations. We've got about 30 visible in the northern hemisphere. If you ever go to the southern hemisphere, you'll find that many of the constellations are really small and kind of silly. Like you know, oh, those 4 stars, okay, I guess, kind of thing. But in the northern hemisphere, these are generally the ones that you're going to be you're going to be focused on. I mean, you should, if you're setting out to learn the night sky, this is a good collection of ones that you want to look at. Now you also notice too that these are divided by season, right? That is because as the Earth is going around the sun, right? We are looking at different, and as its tilt changes, we are looking at different parts of the sky, so we're seeing different constellations at night. Now, this is a fairly big list. Oh wait. Okay. Not what I was intending to do. Sorry, Jedi mind power error. This way we'll let you finish. Or now I. Did somebody do something? Okay, well, hopefully that times out and has some sort of triple on it. Hey, there it goes. Okay, cool. Now, as I was saying, that in the 4 seasons, across the 4 seasons roughly, there are the main constellations that you'll be able to see. However, because of the tilt of, just the fact that the Earth is not wobbling around like a crazy ball, it is, spinning on its axis, right? And it is always pointed in this, toward the same object, right? And so in that point in the northern hemisphere, we're looking directly at Polaris, which is the North Star, right? Now, the nice thing about this is that as these as it's spinning around, this actually results from our latitude, or in most northern latitudes, this results in constellations that are circumpolar. These are constellations that we can see all year round, right? So these are really good constellations to know, because if you know these, then you can go out at any time of night and start using them as guiders for you, right? So Ursa Major, Ursa Minor, Draco, Cepheus, Cassiopeia, and Camelopardalis. Camelopardalis? Never get that right. Okay. So if we are looking, so we're actually to look outside now in January. So we are looking north, right? So there's the North Star. I'll get into easy ways on how to find that in a little bit. But what we can see here is Ursa Minor, Draco, Ursa Major, Cassiopeia, and Cepheus. Right? And so those are the constellations, and that you can go out at any time of the night and be able to see, providing that you don't have any clouds blocking your lights. Right? We move into April, and you'll notice that all that's happened here, you can still see the same constellations: Cassiopeia, Cepheus, Draco, Ursa Minor, Ursa Major, and all that's happened is it's just rotated a little bit, right? And so throughout the seasons, so we get into July, and things have just rotated around. And you'll notice that they're spinning around this little dot here, which again is the North Star. Get into October, same thing. And then back in January, right? So it's basically just spun around. Those are all taken at the same time every single night on some arbitrary date that I picked in those months, right? So those are constellations that are really good to get to know. If you don't, I highly recommend spending some time getting outside, looking up, and familiarizing yourself with those. So, getting back to the easy to find constellations, I'd say there's a handful of ones that you really want to focus on when you're starting out. They're the ones that tend to have the brightest stars in them. They're the most obvious. And they tend to have some very prominent features, right? And or very recognizable patterns. I mean, the funny thing about constellations is that they're really arbitrary, right? Like there's no rhyme or reason for a lot of it. I mean, we lucked out that Orion looks so cool and how he's got the belt and everything, right? But that's an anomaly, right? I mean, I don't know. I mean, I've never, Taurus does not look like a bull. I don't care what you say, it doesn't. So there's a lot of them are definitely stretches of the imagination, right? So what you're going to have to get your brain to do is kind of recognize these, these arbitrary star patterns and kind of map them into your head and remember what they are. That'll take a little bit of time, but if you start out with these basic ones, Botes, Leo, Cygnus, Hercules, Lyra, Sagittarius, Pegasus, Gemini, Orion, and Taurus, those are pretty good. I mean, there's a couple of other ones in here that I could throw out that are useful and easy to pick out, but I think if you really just wanted to focus on some recognizable ones, those are good. Those are good to work with. Others may disagree with. So, let's start talking about a few of these. The constellation Boötes kind of has this kite-looking shape to it, right? Looking like this. It's very identifiable because of the star Arcturus, which is a very, very bright star that is fairly easy to find. And once you've found Arcturus, the rest of Boötes is pretty straightforward. Corona Borealis is also actually really easy to pick out. It kind of sits off on its own a little bit and can act as a good marker for the rest of Boötes, right? One of the things I should caution you too is that when you're looking at this, there's a whole other sky there's a whole other sky that is, existing everywhere else around this tiny slide, right? And you may have a hard time, like this looks easy because there's lines drawn out for you and I've set up the orientation such that it's easy to look at. But when you actually get out there, this is a little harder than you might think, and you kind of get into this problem where everything starts to look like a triangle, and there's triangles everywhere. So having a couple of recognizable pointers, to orient yourself, finding Arcturus is one thing, but then you might start looking off this way, wondering where's the rest of the kite, right? So you know that Corona Borealis is up there, so you can kind of look that way, right? Leo is another easy one to pick out, although a lot of these stars are quite dim. Relatively speaking, Regulus, the bright star, the brightest star in the constellation Leo, is very identifiable. Very easy to pick out. The rest of this, like with this kind of coat hangery kind of thing, is visible. It's very hard to tell from the from the city, but on a dark sky, they do pop up a little bit. The other challenging thing I would say for when you're starting out, trying to find Leo, the distance of these stars from like here to here and here to here can be a little misleading and tough to tell. So, but that's the general shape of it. And you should be able to work your way from that. Behind it, Hercules. Commonly looking at him in the summertime, he's got I always forget that he's upside down. The really recognizable thing in here is actually the keystone. And once you've found these 4 stars, the rest of the constellation tends to be pretty easy to work your way out, because this keystone shape is very recognizable. These stars happen to work out and be nice and bright, so it makes for a good pattern that you can recognize pretty easily. Sagittarius, kind of hard to see from our latitude. But it's a good one to know, especially if you go a little bit further south in the summertime. The thing I love about it, and I think that everyone loves about it, is it actually kind of looks like a teapot, right? And not only that, it's the teapot that's pouring into the Milky Way, right? So all of this haze and stuff that you're seeing here, right? That's our galaxy. That is the galaxy in which our solar system resides and is moving around in, right? And there's this cute little teapot that's pouring into it. Typically, I think you add the milk after, but whatever. It worked out. But yeah, that one you will in the summertime you'll be able to spot it kind of low off in the horizon if there aren't too many trees in your way. So. Yeah, and then getting into the winter, some of the other winter constellations. Orion has got to be the most recognized. I would argue that it is the most recognized constellation. A constellation like Ursa Major, a lot of people know it, but I don't think a lot of people would, if you just pointed them toward Ursa Major, I don't think they would recognize it, or they'd be able to know that that's what they're looking at. Everybody knows when they're looking at Orion. And from Orion, you've got a bunch of really good pointers. Like he's got this really convenient bow, that he's shooting towards, and you can use that kind of to find Taurus, right? Because you can orient yourself and then use that to guide your way up, right? Castor and Pollux, which are the stars in the main stars in Gemini, they can make for, if you ever go hunting for something in here, this makes for a very good reference point in there, right? You can kind of do it in there. And then having Canis Minor over there is so, and it's not just constellations. There are concepts of pointer stars, asterisms, and other things. When we say constellation, we're actually talking about what the International Astronomical Union has defined as these stars shall be part of this constellation, right? So something like the Big Dipper, right, is an asterism, right? The Ursa Major is bigger than the Big Dipper, but the Big Dipper is the thing we all recognize, right? So I'll show you a few of these, and they're really handy. They're really handy. And not only that, one really good point to make here is you don't have to, adhere to the asterisms that the astronomical community has made up. You don't have to call them by what other people call them. You don't have to. You don't have to stick to the same patterns, right? If there's a pattern out there that you find that works for you, stick with it. And actually tell other people about it. I picked up some really cool tips from some people that just happen to have been out in the night sky and found that there's a nice little triangle that helps them find a Messier object or something. So, the classic finding Polaris. This is one. Polaris is one where I think it has such a. There are so many misconceptions. Well, actually, there's one main misconception about Polaris is that somehow people think there needs to be this big, bright, obvious star. The one that. And whenever I show people Polaris for the first time, they are always astounded at how insignificant and boring it is. But the reason why Polaris is so special, right, is because that is the point in the night sky that really doesn't move, because the Earth is spinning around on its axis, with its axis pointed toward Polaris. Right? So that's what makes it special, and that's why it's important. If you end up ever having to polar align a telescope, that's how you're going to do it. Okay? So the way that you want to find Polaris is you find Ursa Major, right? Well, you find the Big Dipper portion of the Ursa Major. Right? So you've got the handle, you've got the cup, right? And then you take these two stars and you go, whoop, and it forms a nice line. Right? I will warn you, straight lines in the sky tend to curve. Okay? There's a little bit, I mean, this one's fairly obvious because there's nothing else that's actually out here. It's one of the nice things about Polaris is that it is actually the one kind of bright-ish star that's out in the middle of nowhere, right? But, I mean, you can even see, like, the way that I drew this is really not quite right either, So these are rough things, so they're never going to be perfect. If you're looking for the constellation of Wotis, so I was telling you earlier that finding Arcturus is really easy, and we get to use Ursa Major again. So again, we take the cup, right, and then we take this curved part of the handle, right, and we curve our way down to Arcturus, right, just right there, like so. Right? So that's an easy one too, and Arcturus is really easy to find as well, just because it's big and bright, so it helps. Again, the other, like I was saying, that straight lines tend to become curved. Short distances tend to become long. So sometimes, if your orientation is a little bit off, you may overshoot and start doing something like this and not really pick up on that somehow. It can happen, So if you find that you're not seeing it, maybe dial yourself back a little bit, kind of thing. For Arcturus, you can actually find Spica quite easily by just carrying along the same path. All right, so let's start Spica, or Spica, down there, in constellation of Virgo. So, just a handy way to kind of use the Big Dipper to get yourself around. N31, the Andromeda Galaxy. There's a couple ways to find this. The one that I always use is I start in Cassiopeia, because Cassiopeia is a really nice either M or W, or sideways M or sideways W, which makes it very easy to orient yourself. Right? So if it's in this W shape, right, what you're going to do is you're going to take this star and this star, right, and you're going to go straight down to there, like that. and then you're going to come up this way. And then you're going over here. And at this point, these stars are getting pretty dim, right? This star in a moderate sky is hard to see. Like, you're not gonna be able to pick this out from the city at all. But even with some light pollution, this gets kind of hard to see. But you're going to go up to there. And the trick that you're going to want to use here is to use a technique called averted vision. So you can actually, so this is cool. I mean, I like showing people this. Some people get it, some people don't. But you're able to see a galaxy outside of our own with your naked eye. So this is something that you can just see with your eyeballs. And I think that's really cool. Like that's, there's a massive galaxy filled with hundreds of billions of stars, and it's visible to the naked eye. So, but the trick is, so getting back to averted vision, the trick that you want to use is you kind of want to look away from it, and I actually find that focusing on this star works really, really well. So you'll focus on that star, and then this will kind of come into perspective. You'll actually be able to pick it up. The reason why averted vision works is because the sensitive part of your eye, you want to look away from the object, right? And the reason why is because the sensitive part of your eye is actually on the outside. It's a common psychological problem in astronomy, especially when you're hunting for really faint objects, and you're using averted vision, and then it just kind of pops into view. You get this little faint smudge, and then your immediate reaction is to look directly at it, and it's gone. Right? So it's a technique that you have to train yourself to do a little bit, but it's quite handy. The summer triangle, it shows up in the summer. It's formed of these three bright stars, Deneb, Vega, and Altair. I'll actually also note that this asterism will actually continue to show itself into the fall, just because the nights are getting longer. So it's kind of like the summer-autumn triangle, really. And I guess, yeah. But this is a good one. There's a lot of really cool stuff in here. This is a really good area of space to know. There's some nice nebulas in there. There's some really nice double stars in there. There's a lot of really cool stuff that you can see with some very basic astronomy equipment. So this is a good one to know. This is just a section known as the Great Diamond. Just using these 4 stars. Again, just a way to orient yourself, right? So, like I was saying, sometimes it can be hard to tell distances. Sometimes you've gone way too far and you haven't realized it. Using asterisms like this, you can kind of reorient yourself. So if you're looking at a star chart and you can kind of draw these lines out in your mind, it's like, okay, well, it's got to be in there somewhere, right? And you know that if you have your telescope pointed out here, that you may have gone a little too far. Right? So you can kind of bring yourself back. Pegasus. Pegasus is just it's a nice constellation, but it's got this this square here. Funny enough, this isn't part of Andromeda. Go figure. But the square is really nice. Okay. So, the ecliptic. So this is the line that is formed effectively by the sun as it traces its path out through the sky. And this is the line that because they're all in the same plane, the line that the planets follow, that the moon roughly follows, right? So if you're looking for planets, the ecliptic is the place to look, right? You'll also recognize some of these constellation names already, like Leo, Virgo, Libra. So these are the constellations of the zodiac, right? I actually, when I was just putting this, I put this presentation together a couple years ago, but when I was reviewing it, I actually had a funny thought. What would have happened if the constellation Boötes had actually ended up in the zodiac? Like, I just had this funny thought in my mind of having to say, so what's your constellation? Oh, booty? which I don't, and it made me think that maybe, you know, astrology wouldn't have caught on so much. But. So, yeah, so if you're looking for planets, right? So this is where you will find them, is along this line, right? The other tricky part to this, though, is that sometimes these planets, because they will move, right? They can get close to other stars. So earlier I was showing you how to find Spica, and sometimes when you think you may have found Spica, you're actually looking at a planet, right? They can have similar brightnesses. The colors will be a little bit different, but to your eye, like it might be a little tough to pick that out. Bright ascension is a subject I'm not going to get into very much, but just to let you know that it's a thing. Bright ascension is actually a coordinate that we use. So there are two coordinates that we use to definitively define where an object is. We have two numbers that say this is the latitude and longitude of this number, right? Just like you would on the face of the globe, right? These are your coordinates, right? So the coordinates of an object are defined by its declination and right ascension. Declination is just a straight up and down, right? So I'm looking south, right? And declination is just a straight up and down amount. Right ascension is trickier because it's this left to right, east to west kind of thing. The problem with right ascension is that the Earth keeps spinning. So what it means though is that the coordinates of right ascension are going to stay the same, and then where that coordinate of right ascension shows up differs throughout the year, right? So as you're looking this up, right? So the reason why I mention this is because it's actually kind of just a handy lookup thing. So if there's a list of objects, sometimes they'll have constellations, and that's handy too. But many times they'll actually list their right ascension, right? And actually, and quite likely their declination as well. But the right ascension can be a very handy tool to use because it's just a quick reference to, like, if you're looking for, like, so I went on a hunt for double stars a few years back, right? Just, I don't know, it was a fun thing to do, right? So I had a list of them, and it was very easy to just take the right ascension and know this is, you know, if the right ascension is from 8 hours to 15 hours, that means it'll be in the night sky in the springtime. 15 hours to 20 hours will be in the night sky in the summertime, and so on, right? So it's just a handy reference. You don't need to get into the depths of how right ascension, hour angle, and sidereal time and all that stuff works, but it can be a good reference for you. As I was talking about, when you get out into night sky, some stars are brighter than others, and conversely, some stars are different than others. And the numbers that you'll see are referred to as magnitude, right? So you'll see these numbers used a lot to define how bright a star is. So these are the stars in the constellation. These are the stars in the constellation Orion. The thing about magnitudes is that because astronomy is dumb sometimes, the brighter the star is, the lower the number. And this goes into the negatives. We'll get into that some other time in another talk as to why that happened. But the higher the number, the dimmer it is. So to give you some reference, if you're familiar with the star Vega, which is a really bright star, you know, it's -1, you know, kind of, so between 0 and -1, I think. And then you know, the limiting in a good dark sky, roughly the limiting number that you can see is about a 6. Pluto is like a 14, right? Good luck ever seeing it. So if you're looking for stars and you have a kind of if you're looking for objects and you have that list of numbers, you can use that to kind of tell where you can take it. I recommend using some planetarium software. I put all these slides together using Stellarium. Its UI is, we'll just call it clunky. But it's functional. It works. I recommend using it. It's free and open source. Starry Night is fantastic. I've used that in the past too. It's a paid product, but it's worth it. It's got a lot of really cool features and stuff. But really, what you want to do is it's a good tool to use to plan out your night a little bit. I highly recommend, if you're going to go out and observe, that you take the time during the day, when you have all the light in front of you and your computer and everything, to plan out your night, as opposed to showing up late at night and realizing you have forgotten something or you didn't know. From the back?
I just wanted to mention that card is CL.
Yep.
The other software is we want.
Yep. There's a couple of, so Carte CL is another one, or Centered Universe is one as well, but that one's kind of old.
You pay for ECU.
Oh yeah, you pay for ECU as well.
Card CL is a free one.
Yeah, so Carte CL is a free planetarium software. Yeah, go ahead, Paul.
C2A is another one.
Yeah, yeah.
That one is pretty expensive.
So there's a number of options out there for you, but recommend using them. Get familiar with them. So if you're going to be getting out into the night sky, there are some really basic things that you can do to prep yourself. These are all really good questions to ask. When I say M objects, I'm talking about the Messier objects, the list of Messier objects. Things like the ISS going over are just kind of cool. Same with the Iridium flares, right? Although eventually those are going to go away. But those are neat. Especially if you're doing any kind of photography, these are good to know about because they're just careful in your shot. Check the aurora. This can be a good or bad thing depending on what you're trying to do. And who else is going? Astronomy doesn't have to be a lonely experience, right? You can hang out and be nice and quiet with your friends out under the night sky. Your equipment, definitely want to make sure that you have a red flashlight. More importantly, have a white flashlight. I can't tell you how many times I have gone out with only red. This is really hard when you realize that you need to tear everything down and you can't find that thing that you just dropped on the ground. So, if you're going like a planisphere, paper charts, logbook, definitely take recordings of anything that you see. It's fun to look back later on and just compare your observations. Binoculars, bring an extra layer of clothes. If you're going out now, obviously, but even in the summertime, one of the things about observing is that you're not moving a heck of a lot. You're kind of just standing there looking up, or even laying down on a chair and looking up. Your body gets kind of cold. So definitely recommend being prepared on the weather side. Yeah, chair, stool, spare batteries as always. So.
Warm room key.
Warm room key, if you're down at Glenley. If you forget the warm room key, that's really going to suck, especially when it's minus 30 out. Yeah, so that's everything I had. I ran a little bit over time, but that doesn't matter because I'm running the show. Thank you. Oh, hello. Good evening, and welcome to the Winnipeg Royal Astronomical Society of Canada, Winnipeg Centre of the Royal Astronomical Society of Canada, our meeting for January 2018. We are not quite officially living in the future, but we're getting there. My name is Brendan. I'm somehow the current president of this fine club. Do we have anybody out for the first time? Newbies, put your hand up. Hey, look at that. There are quite a few of you. Awesome. Council members. Make yourselves known. Somehow, put your hands up. New people, meet council members. Council members, meet new people. Catch up with the refreshment break, or just come talk to me too. On the schedule for tonight, we just went through this riveting beginner session, how to find stuff in the sky. I'll have to get that guy out again. I'll run through some announcements. We will have our annual general meeting. So for the new people, I do apologize. This is the one night of our 12 meetings that we have every year, minus the barbecue, where we actually deal with club business. So hopefully it'll be quick and painless. And then we'll have a What's Up with Brian and a What's New with Ian. So What's Up is going to be what's up in the night sky. We're clever. And what's new is what's new in the science and astronomy. And yeah, probably around, I don't know, in between, probably around 8:15 or so. If things are on schedule, they'll probably be closer to 8:30. We'll have our refreshment break, and then we'll come back at 9 o'clock for our feature presentation. We've worked with the University of Manitoba and their Department of Physics and Astronomy to bring in Dr. Craig Henke, and he will be giving us a talk on globular clusters and their weird binary stars. I had the pleasure of joining him for, we went out for dinner last night, and I got to ask him a bunch of cool questions, and I'm really looking forward to his talk. It should be pretty good. So, moving on to the announcements. We have an outreach opportunity. There's a winter wedding happening at Fort White. They've actually they've offered us they've offered us a donation, and I thought it was kind of cute and romantic, so I said yes. Yeah, whatever. But I think like I could use. I mean, so I'll go by myself if I have to. No big deal. But if somebody wants to join me, that'd be appreciated. Let me know. It's not going to be a ton of. It's probably going to be cold. If it's cloudy, we'll just have to call it off. No big deal. But if there's, I think there's probably going to be about 50 people or so. Now, I'm not anticipating massive lines at the telescope, and I'm also anticipating people kind of mingling inside, and then the two of us can tag off or come in and out or something like that. So, but we'll work. If you're interested, just shoot me an email or come talk to me at the break, and we'll work something out. I think so. Yeah. Yeah. I didn't actually get to pick the date, unfortunately. They seem to have they seem to have already decided it before they got in touch with me. I know, right? Priorities, people. Actually, funny story. When I went to New Zealand for my honeymoon, a lot of it was centered around when the moon phase was. My wife is a wonderful woman. Yeah. Anyway, yeah, I mean, she's very good. So photo exhibit. This is something that Ralph Kroning is organizing. At the Millennium Library, there's a gallery, and you can show off your cool astrophotographs. So if you're interested, get in touch with Ralph. You can also talk to me. I will hook you up with him if you don't know who he is. So take care of that. I don't know what to call this. I mean, I guess that's our wintertime potluck. We can't really do a potluck around the holidays because everyone's doing stuff with their families for some reason. So as a club, we like to get together, and we will be doing it this year at Jane Judy's, which is almost becoming tradition at this point. That'll be, not that I'm complaining, it's a great place, I love it. But it's a 189 Kingsway. It'll be on Saturday, January 27th. The actual time of it hasn't been determined.
6 or later.
It'll be 6 or later. Okay, so it's been determined. So 6 p.m. or later. Come on out. Bring food, beverages, and good times, and yeah, enjoy the company of your fellow club members. This came my way via the website. I have honestly not actually looked into it too much. I will send this out. I will send this out to a list, but it seemed cool. It seemed like just a neat thing. I don't know that I felt like I would just pass along to the club. So my apologies for not having a ton of detail on this, but there's quite a lot up on that slide. So I'll send this out to the mailing list, and you guys can get all the information. But yeah. Okamic March Astronomy Night is continuing, despite the weather. They will be, I mean, they've got an indoor part to it at least. So the next one is on Thursday, January 18th. As usual, if you are a club member, they will let you in. If you're a club member with a telescope and you're helping out, those are the conditions, they'll let you in for free. So they'll waive the fee. So head on out. It's usually a good time. Danielle Hood has taken over from Jennifer West on the open houses, so she was doing that last year, and then they did renovations, and now she's starting it back up again. So beginning at the end of this month, so last Wednesday of every month, there'll be an open house at the Lockhart Planetarium, which is on campus here. So it's not the Manitoba Museum Planetarium, it's the one at the U of M campus. And I know she appreciates having some RASC members out just to help. Right? So if you're interested, talk to her, or just show up on January 31st. Telescope loans. We actually just got the solar scope back. And Stan, do you have any other updates?
Yeah, the two scopes are both spoken for at this time. So.
Okay. So if you want to get your name in to borrow a telescope, if you're a club member, talk to Stan. He's at the back there, and he will get you into the queue. I don't really know how he manages that, but he does seem to. Yes, Stan?
Yeah, I promised to do an article for the next month's newsletter that'll explain what scopes are available. So for anybody who's newer, that will come out very shortly.
Excellent.
Explain what's available.
Excellent. Okay, thanks, Stan. Glenley Observatory. This is our observatory south of the city, just, I don't know, 15 minutes south of the perimeter. If you're a club member, you can get access. There's a warm room key that you can use with key access. So it will be locked, but you can get a key from our observatory director, Brian, who's being lit up by that laptop over there. Probably yeah. It made you really easy to point out. Yeah, so it's a good facility. I recommend taking advantage of it. And yeah, I was also going to add that Brian was thinking about doing he was considering doing a members' night, but then he said something about ludicrous cold. No, I'm not going to do it. Ludicrous cold. So no members' night this month. Okay, so that's it for announcements. I'm going to jump into the annual general meeting. So, like I said, I'm hoping this is quick. So on the agenda, we've got a report on center activities for 2017. I'll give you a status of our current council, and then we'll do some elections. We actually only have 2 spots open, and they're both councillor positions. But I thought I'd give you a rundown of what we did in 2017 at a pretty high level. We continued our streak, I guess. I don't know, these things just kind of seem to happen on their own. But with the help of many people. But we had our 12 monthly meetings. We had 10 held here at the U of M. We did one at the planetarium downtown, which was cool. And then we had our typical barbecue, and we used the external speaker fund to bring in Dr. William McKinnon, and he was actually a project scientist on the New Horizons spacecraft, and stood up here for an hour and filled our brains with geology of Pluto, and I've never been more fascinated by geology in my life. It was incredible. So that was a real highlight, definitely. We did a bunch of outreach. We had our astronomy day out at chapters. There was a Whiteshell Public event that Mike Caracas organized, and we're going to be doing a bigger one next year, so it's good to see some growth there. This IM Festival thing is something that I kind of got hooked up with, and we're hoping to do a little more with that next year as well. They're just it's one of those wellness festivals, and they thought having us out would be cool, and so it seemed to be a good match, and so I'd like to do a little more of it. We continued our excellent relationship with Spruce Woods, thanks to the Spruce Woods Committee for doing all that hard work. We had their public event out there as our way of saying thank you, and then we had our Spruce Woods Summer Party in a very, very wet September. I think my tent is still drying out. But it was a fun time. We had a lot of fun. So, if you've ever wondered what your council looks like, these are the people that make things happen behind the scenes and take care of a lot of stuff. There are two classes of positions that we have on council. We have our elected positions. Those require these general meetings where we'll have a vote, or not in most cases. And then there are appointed positions. Excuse me. Appointed positions are positions that are appointed by council. Crazy, right? So right now I'll just run through the appointed ones. We have a national rep in Dennis Lyons. We do have space for a second national rep. I don't know that we have necessarily. I don't know that we need to really fill it at the moment, but that's something that council can figure out if they like. Dennis can certainly chime in on that too. Our Spruce Woods Star Party organizer is still Sylvia. I don't know how long that'll be. She'll keep doing that. We brought on a new webmaster, Kevin McGregor. I have been somewhat neglectful of working with him to try and move some things forward with the website, but believe me, it's going to happen. And then our Wincentrics editors, it's being shared by Mike Practice and Abdul Al-Mani. Abdul is actually also the guy that films all of our all of the meetings that we have and throws them up on YouTube, so you can hear all the same stupid jokes that I tell you every month and watch them over and over again. And then, as I was saying, our observatory director is Brian. So, on the elected positions, so me, Brian, is our current vice president, so I've got one more year of doing this. He's got one more year of doing this. Our treasurer is Stan, our secretary is Cliff, and then our councilors are here. So these will be coming up at the end of, at the next AGM, which will be a year from now. But these are two open positions for councilors. So, I have received two nominations. Megan Ostrom, who is currently a councilor. She's been a councilor for 2 years now, and she is running for re-election. And then Neil Wise was nominated as well. I got that via email, and I've confirmed that she wants to stand for election. So, I just need to ask if there are any others. If there are any other nominations for one of our councilor positions? Okay. Repeat that again. Are there any nominations for our councilor position? Okay. And with that, congrats, Gail. Welcome back, Megan. Okay, so that is the AGM. Unless anybody else has any other business they want to bring up. We didn't get a financial report because Stan just got in from somewhere warm at 4 a.m.
No excuse.
I know, right? What's up, Stan?
One person had asked me to save a calendar for him. I have it,
Okay.
so they can approach me at the break.
Okay. If you want a calendar, and you are that person, go see Stan. Also, as is becoming very common, we've got a bunch of old magazines and stuff. There's some really ancient stuff from 1995. Yeah, you heard me. I said ancient. Yeah, feel free to come pick those up at the break. So, I think we're good though. Okay, so in that case, then Brian, you're up.
right. So this is, let me stay on the right. Okay. Anyways, I don't know how this is going to work out. Okay, so this is what's up for January. Put a lot of thought into this one. Just nice to take a little break from it. All right, so Mercury. Oh, we don't have much to say for Mercury. It's basically a day planet. Dawn. Next we have Venus. Venus is a little too close to the sun to really do any observing for it, but we'll show you something nice. Mars is coming up this year, so I'll talk a little bit more about it. The nice thing about Mars is I think it's supposed to be about 23 arcs across almost, so it's been pretty close. Mars is one of my favorite planets. We'll talk more about that later. It was pretty close to Jupiter on January the 9th of this month. Of course, Jupiter was pretty close with Mars. Not much to say about Jupiter again. It's mostly kind of a dawn date planet kind of thing. Saturn. What nice about Saturn is it's hooking up with tomorrow actually with Mercury, and according to this, we should be able to see both the planets, which is behind. I've seen Mercury before, but it'd be interesting to see how Mercury looks through a telescope. Okay. Of course, this is kind of a top view representation of our solar system. You can kind of see the planets are congregating around about here. So Mars will be around about here. It's be July the 7th, I believe. Should be right about there, along with Earth. So, and of course, Jupiter and Saturn doesn't really move much. Okay, so what do I have here? I have, of course, I said around 7 o'clock. I was playing around Solarium before. We have the Moon, Jupiter, and Mars. There's Mars and Jupiter, so that's pretty much there's your new moon right there. They won't move much throughout the better part of the month. What else I have? Then I kind of figured out, okay, what's later on today? I picked January the 14th just to see what's going to happen for the sole purpose of, I have no work to, so I'll be free on January the 14th to see how this actually works out. So we have Saturn and we have Mercury, and we also have the Moon as well. And of course we have Mars and Jupiter. And of course there's Venus over here. It's, again, too close to the Sun. That's kind of interesting. To me, that's all the planets on one part of the sky there. Next we have what's going to occur for the better part of January for the events. Not much really happening. We do have of course, the new moon on the 17th. We do have a double shadow transit on Jupiter. And of course, the total lunar eclipse that's going to happen on the 31st. I'll talk more about that later. It's not going to be very much to look at because it's pretty close to the dawn, right to the horizon. Okay, now I was kind of looking through Sky News, and this is my top 5 events for 2018. Number 5, well, total lunar eclipse. Not that great, of course. I like my 2 comets, number 3 and number 4. One, September the 5th, it was the 10th, right? They said the magnitude between 4 and 7. Hopefully it's a 4, but it turns out to be a 4. That's great because it's going to be a little warmer, but it's kind of like more in the late night. Then the comet 46P, a magnitude of 3, which is pretty good for a comet if you ask me. But it'll be the evening sky, but of course, dead of winter if you ask me, a little too cold. April the 2nd, we have Mars and Jupiter, Mars and Saturn. My 2 favorite planets. This is my 2 favorite planets, and I'm surprised that they're going to meet up on April the 2nd. And of course, my favorite, Mars again. We're going to hit 24.3 arcs, but unfortunately it's going to be low in the sky. I'll talk more about that later. Of course, Mars, we circle around every 2 years, we catch up with Mars. Okay, now there's a little bit of information about, anyways, a little information about the total eclipse. So you see it's pretty early in the day for us to really do the observing, but we'll see how it turns out. I did a little video on this to see how it looks. So, the way it looks, okay, so we're about, well, anyway, looking at about 7 o'clock, it'll be below the horizon before any of us are able to see the totality of the lunar eclipse. But what I'm going to do is, hopefully this works. Okay, there we go. This should play automatically this time, so there should be no problem. So that's the moon. That's when the eclipse is starting to happen. So this is roughly 6 o'clock. Hopefully it is playing. We'll see. We'll find out. It's supposed to be really bad here. You don't have to press anything. I swear to God, it's going to work. Yeah, it's working right there. See the minutes there?
It's in real time.
Yeah. No. I started recording this. Okay, so don't worry. It's going to speed up. You can see an arrow. There we go. And I'm going to speed up a little bit. This is going to give you an idea of how it's supposed to look like, and in relation to when dawn's supposed to happen, and then that's the horizon, of course. And see how it works out. And kind of pause it there. That should be the totality of the lunar eclipse right about there. Of course, we're pretty close to the horizon. You know, the sun's coming up, right? Sun's over here, and of course, it's going to fade out. I just want to see what's going to look like, if it's worth it. So on Wednesday, January 31st, probably Glen Lee would be the best place to look at it because you have a warm room to deal with, and of course, there should be nothing obstructing your horizon at that point. Next, I'm going to just talk a little bit about my favorite planet, Mars. Okay, so I did play around with Solarium right here, and it worked out to be August the 31st is probably the best time. That's the closest point Mars is going to get to Earth. I know Sky News says July, but I guess when it gets close enough, you do any observing. But at 24.3 arcs, that's pretty big, past me. Should see a lot of surface detail on Mars. Of course, unfortunately, Mars is pretty low in the sky. It's what, 24 degrees above the horizon. So hopefully, we do get some, unless you move further south, like in Arizona or something like that, then you'll be able to see Mars much better. But unfortunately, for us, we're only at 24 degrees. Okay, so, and I think that's it. That's all I have to say.
Brian, an interesting factoid in your January list of events, you had 2 full moons.
Do I?
Yeah, correct.
Well, there is. Oh.
It is happening.
Believe it or not, Jay's not correct.
Well,
No, that's right. But it is 2 full
there's
moons.
also 2 full moons in March, but there are no full moons in February. It takes 29 and a half days between full moons. It's an event that repeats every 19 years.
19 years, good to know.
Thanks, Brian.
All right, thanks.
By the way, this is the part of the meeting where we switch over to the Mac. And I get to make jokes about it.
You're not making any jokes.
I thought I'd let you off easy this time. Actually, the only one I can think of right now has to do with a one button mouse click, and that doesn't really apply here. So you guys finally moved on from that. Sorry about the blinding light. I know you're all dark adapted right now.
Breaking bits of it off. Fire.
I recognize it's on, by the way. We're switching to Plan B. Oh, okay. Okay, so we're switching to the other Plan B.
Buy Ian a PC.
Piece of cable.
I'm just going to warn you though, Plan C is actually another Mac.
There we go.
So, if you're curious what just happened there, we took the exact same cable and reversed it. Last I checked, electrons were happy to flow either way along those cables. We got the special mono, like, yeah, I guess maybe that's what mono cables are? Sorry, okay, mono direction. Sorry, that was way too terrible, sorry, I really apologize. Anyway, okay, so after all that, thanks for waiting. So Ian is going to give us an update on what's new in the science of astronomy.
Good. Let's stick this in the pocket. Find an appropriate point of attachment. You can all hear me well. And so it's what's new for January 2018. And I'm going to talk about peas in a pod.
I'm playing your game again.
Okay. You may have seen this picture before. Okay, so this is a picture, well, an artist's representation of the TRAPPIST-1 system. And I talked about that quite some time ago. And there's quite a bit of detail that you can get on the planets themselves, how they're strung out, their relative sizes, and so on. Well, rather than just having a look at one system, okay, somebody decided to have a look at a lot of systems, all right? And so what people did was to have a look at something of the order of, what was it? Yes, 909 exoplanets in 355 systems. This is from the Kepler survey. And what they found was something very interesting. That's that if you have a look at the individual exoplanets within a particular system, they tend to be the same size as their neighbors. And the exoplanets which are orbiting a given host star have a nice regular spacing, orbital spacing. You notice that that doesn't work for our system, our solar system. The inner solar system is a little bit different, and there seems to be a lot of evidence anyways that Jupiter and Saturn have messed things up. Okay? And so one of the very interesting things they found about these systems is they're not that messed up. All right? And so they're actually going to expand the search a little bit for looking for ones where you've got basically a mix of planets. We've got Jupiter-sized systems as well, and have a detailed look at their spacings and sizes and so on. So that was kind of a very interesting result. Now, one of the interesting things about the Kepler photometric data, and I'll show you a little graph, a little indication of what that data actually looks like, but I'll show you an anomalous one. I mean, a lot of this stuff is searched through by computer, okay, fairly regularly. Now, the nice thing about doing analysis, if you like, via the computer is that it will find stuff that you expect to find, right? Because that's what you're programming all the time. If, on the other hand, you want to have a look at that data and find things which are a little bit unexpected, what you might do then is to have a little bit of human intervention. And that brings us to our next story. Maybe it brings us to our next story. It still doesn't want to bring us to our next story. Ah, there we go. All right? And there's an actual project called Planet Hunters, where we actually get people to have a look at the Kepler data. And they found one particular instance where they actually did find, well, one thing, okay, they actually did find planets around some systems that the computer missed. And the other thing is that they found a rather interesting trace. And this is for 4628552, or otherwise known as the WTF star. And that was sort of a little tongue-in-cheek because what happened was that the investigators, the principal investigator in charge of the Planet Hunters project, decided to publish the results, even though there was nothing really to say other than the fact we don't have a clue what's going on. All right? And they entitled it, Where's the Flux? And of course, it has such a cool acronym which can be reinterpreted appropriately because they didn't have a clue what was going on. And this is the reason why they didn't have a clue as to what was going on. Typically, if you have a look at the data, and it's coming from Kepler, supposing that you were to have a look at the sun, for instance, and you had a Jupiter-sized object pass in front. What would happen is that you would see something like a 1% dip in the light curve. So over here, okay, where we've got, basically these are day numbers along here, basically the observation day number that the Kepler was looking at this particular object. Okay, you see those tiny little dips up there, all right, and they occur somewhat irregularly. And then something rather interesting occurs rather dramatically around about day 100, 800, and then some really startling stuff shows up over here. well, the Planet Hunters brought this to the attention of the principal investigator, and of course, they wondered what the heck was going on with this particular star. This star is not terribly different from the Sun. It's an F-type star, so it's a little bit hotter, a little bit larger, okay? And it's a reasonable distance away, about 300 parsecs. If you have a look at the traces in a little bit more detail, the startling thing about this is that in the upper corner there, you see something like a 20% dip in the light curve. Over here, something like 15%, and then down here at the bottom, something like an 8% dip. And of course, things are happening in a variety of different fashions. You see a nice, almost symmetrical dip over here. Here you see some irregular kinds of things going on. So, of course, when you're confronted with data like this, you wonder, well, okay, what's going on? And so you try to build some models of what's going on. This star is affectionately known as Tabby Star, named after the principal investigator, Tabitha. And this is an artist's impression of perhaps one of the things that might be going on. Here you've got dust, circumstellar dust ring, if you like, going around it. Another thing is another suggested possibility for explaining the observations. It was that you had a swarm of comets. All right, so you're seeing this basically dimming of light due to the swarm of comets. The problem is that you don't, well, you might need a couple of hundred comets or so just to take care of the individual dips, but what it really needs to know is what do you need in total. Well, you need thousands or tens of thousands of comets sort of moving around. So that might work. All right. The other thing that you might try is, okay, so we've got basically a protoplanetary disk, but one of the things that we know about these kinds of stars is that maybe it's a little long in the tooth to expect to see those kinds of things. It could be, all right, that we have collisions of protoplanets, all right, and that doesn't work too terribly well either. So now you get the idea of why they're calling it what? The WTF star, right? Everything sort of goes out the window there. And then, of course, the more fanciful ones, okay, is say, we're looking at, advanced civilizations, and here we have basically a carry-on from the Dyson sphere. The civilization is dying, builds a huge structure around the sun to catch the host star, to catch the energy, or what you do is you produce a whole bunch of these things, so we've got something called a Dyson swarm. People actually, they were rather intrigued with this, and of course when this notion hit the papers, everybody got really excited. And it turns out that CT did get involved, just as a matter of course. So the issue with the Kepler observations, of course, is that, it sits on a target for a while, or a variety of targets, and then it moves on to another kind of project. All right? So you're left with this sort of tantalizing puzzle. What is it going to do? What you really need to do in this particular instance is to continuously monitor what's going on with this star. And the natural thing to do, okay, is perhaps to draw upon the amateur community. And so we've got the AAVSO sort of involved with observations. And they do a pretty good job. And here's typically sort of the spread in the observations, and you might sort of get it down to 0.05 magnitudes or something like this. But the problem is it's not quite good enough, okay, for the kinds of things that you'd like to do. What you'd like to do is to monitor it sort of continuously. When you know something is going on, then you get a chance for when it's doing these kinds of things, which you saw from that very first trace, is that it happens somewhat irregularly. regularly, okay? It's not nice and periodically, so you know when to time your observations or whatever. You basically have to wait until something happens. And the way they approach the problem, investigators approach the problem, is they started a Kickstarter. Okay, a little crowdfunding astronomy required. They found that you could tie in, actually, to a global network of telescopes, for which, in fact, some time was already donated, but they'd like to do it for a year. Okay, so what they did is basically engage the LCOGTN. You figure out what that is. And through the crowdfunding, through the Kickstarter, 1,762 backers pledged to the tune of $107,421. And then basically what that allowed them to do then was to pay expenses for, I think 2 hours a night. All right? And this is a network of telescopes around the globe. All right? So you can monitor this basically sort of 24/7. And what does that allow you to do is, well, you find out when something interesting is happening, and then you train one of your larger telescopes on it. You do some spectroscopy, you do some polarimetry, you do some filtering, and that way you're able to exclude certain things that might happen. And indeed, okay, they actually managed to do that. So, what's the upshot? The upshot, it is indeed dust. Okay, so sorry, as a little poem suggests, no ET, it's just dust that we see. But what that does is it's probably one of the first crowd-funded astronomy projects around, okay, from which, if you like, you've got very valuable scientific results. Okay. Now, what galaxy is not far away? But this one is really at a reasonable sort of distance, okay? And what we're really interested in, of course, is this phenomena of fast radio bursts. We can actually say something about these things for sure, which is the really kind of interesting thing. It's pinpointed, okay, to a dwarf, source to a dwarf galaxy, okay, about 3 billion light years away. Because it is a repeating burster, that means, in fact, that you get a chance to, in essence, to triangulate on it. Okay, you can train a number of telescopes on it. You can determine its location precisely in the sky, and you can identify also a radio source with which it is coincident. All right, and from that, okay, you can make sort of observations, and we know that from what's called the Faraday rotation measure, okay, basically we're having a look at polarized energy, okay, that's coming from this thing, and it has a large Faraday rotation measure. It's highly variable. It's strong. You can conclude, or at least build a preliminary model that says you've got a neutron star orbiting around a black hole. That's probably a little bit provisional, but one of the things that you can say is that this is in an extreme environment, strong magnetic fields, and of course, lots of charged particles. Okay. I figured I needed another acronym. Okay. Arizona's dark skies. It's nice to have a picture of Arizona's dark skies, right? That's where we all wish we were, right? One of the interesting things, of course, is that we're becoming much more aware of light pollution. Right? And it's starting to make its presence known. Okay, even in Arizona. So here's the sky globe from Meteor Crater in Arizona. You can make out various sources: Winslow, Phoenix, and Flagstaff. And Flagstaff, of course, prides itself in keeping the light pollution low. That brings me to the end of January's presentation.
Thanks, Ian. Are there any questions? Any of the stuff you just talked about? All right, cool. Yeah. Actually, I was really happy with that Kickstarter because I thought it was somewhat fitting, because those initial discoveries were actually, as Ian was talking about, were found by a large number of just volunteers, and they were just trying to find interesting data in this set of Kepler data, right? And as a group, a whole bunch of other people got together and put up some money to just kind of make this happen. So it was and they've obviously bored fruits from that. So it's kind of a nice confluence of I don't know, community, I guess. So we're going to take a break. We'll come back at about say 5 to 9, and we'll carry on with our future presentation. Welcome back. One quick announcement. So if you were here a couple of months ago, I gave a talk on the discovery of Neptune, which is a fascinating little piece of astronomical history. I said that there was a book called the Neptune File, and that I based most of that talk off of, and somebody has actually offered up their copy as another loaner. So if you're interested in reading it, just come down after the meeting. I'll have the book here, and it's, you know, feel free to take it for however long you need, and then bring it back some other time for someone else to have a read. So that is the thing that's available. Tonight, we are very fortunate to have a guest speaker. He will be giving us a talk on globular clusters and their weird binary stars. I actually went for dinner with him last night, anticipating, he had a quick little evening, dinner, I'll be able to get home and get everything ready for this meeting. We ended up talking about globular clusters and neutron stars. He did most of that side of talking. I asked most of the questions, for a good couple hours. It was a very enjoyable evening. So I am actually really looking forward to this. So I'm quite excited. Just to tell you a little bit about him, Craig Heinke is an associate professor of physics at the University of Alberta. His research focuses on neutron stars, X-ray binaries, and globular clusters. Dr. Heinke uses a range of telescopes, particularly X-ray observatories, but also optical, infrared, and radio telescopes. He did his PhD at Harvard and postdocs at Northwestern University, Illinois, and the University of Virginia before joining the University of Alberta in 2008. You could join me in welcoming Dr. Heinke. Thank you very much. I've heard that this RASC Center is particularly likely to ask questions. I think that's fantastic. So do ask questions when you come up. So yeah, I'll tell you about exotic binaries and globular clusters. So first, you are well aware, and I realize now that if I walk over there, I'm right in the path of this, so I shouldn't do that. But globular clusters, I think. Yes, go ahead. Thank you. That's an important question. Do you remember how to turn the mic on? Yes, I do.
Okay, thank you very much.
There we go.
Much better. Now, more than just the three people around me. Okay, yeah. So globular clusters, I think, are the best things to show random people through a telescope for the first thing. So they're 10,000 to 10 million stars, and about 10 to 13 billion years old. And the particular thing that's really relevant in terms of understanding X-ray binaries, we'll get to in a minute, is that the central densities in globular clusters can be about up to 1 million times that of our local neighborhood around here. So much more likely to have some kind of stellar interaction. So now to just go through a little bit of understanding stellar evolution as applies to globular clusters, it's more fun to actually show you rather than tell you. So this is a really neat sequence of images using this observation of the globular cluster over Centauri, which was done by the other J. Anderson. I understand there's another J. Anderson. Probably gets this time.
My evil twin.
Yes. So this J. Anderson is at the Space Telescope Science Institute working with the Hubble Space Telescope. So this is a piece of the center of the globular cluster Omega Centauri, taken with 3 different filters from the near infrared at about 814 nanometers over to 225 nanometers in the near ultraviolet, and so just with the red being red and so on to the blue. So here's a little piece of that image, and now what we're going to do is we're just going to actually sort these stars by color, moving the red ones this way and the blue ones this way. And then we're going to take that same image and then sort them also by brightness. Like that, leaving us with a color magnitude diagram. I think this is one of the sweetest little pieces of sequences that I've seen. And so now, for those of you who this is a good refresher, so we have the main sequence here where stars are burning hydrogen in their cores from the massive stars. They're about the mass of our sun, because all the stars in the globular cluster are to first order born at about the same time, at 10 billion years ago or 13 billion years ago or so. So the stars around here are about the same mass as our sun, and they go down to much lower mass stars, down to a few tenths of a solar mass. And then the stars that would be a little bit more massive than this have used up the hydrogen in their cores, and so their cores start to collapse down, and instead they burn hydrogen in a little shell around that, which changes the structure of the star and causes it to expand up to become a red giant. After some time doing that, then they ignite, if they're enough mass, they ignite burning of helium in their cores, and the star readjusts its structure and goes over to the horizontal branch over here. And then when they eventually run out of helium, then they will, after a short period going up again into the red giant area, then come down and become fainter and dimmer as they go down as a white dwarf. So that's a really neat sequence that I love to show. So now, what happens after they run out of fuel? So for the low mass stars like our sun and so on, then at the end of their lives they become planetary nebulae, which are of course also terribly fun things to watch in small telescopes. And for the stars that are more massive, more than about 8 times the sun's mass, those end their lives in a more drastic event, which I'll get to in a minute because I forgot to move this slide up. So what are we left with after a star comes to the end of its life and can no longer burn hydrogen or whatever other elements they can get to, depending on its mass? Then we're left with what we call degenerate stars, or compact objects. So the lowest mass of these are the white dwarfs, which are supported by the pressure of electrons against one another. And these typically are about the same size as the Earth, and have something like the sun's mass or less. If you have more massive stars, greater than about 8 times the sun's mass, then when they reach the end of their lives, they've been able to burn through additional elements and get up to maybe iron or so. When they collapse, they produce what we call a neutron star. And neutron stars are about the size of Winnipeg or Edmonton or thereabouts, 10 to 13 kilometer radius. In those cases, the electrons are largely forced into the protons, so that the majority of the star is made up of neutrons. And they tend to be of the order of 1.2 to 2 times the mass of the sun. And then the most massive stars, of course, produce black holes when they reach the end of their lives. There we have a total collapse to a point, stars are getting down. So these are several times the mass of the sun. And also, this was not predicted by astronomers before we discovered it, there are giant supermassive black holes in the centers of galaxies. So here's this illustration of the idea of a supernova, that you have the center parts of a more massive star. Instead of just ending with helium burning, you can then go through the burning of carbon and oxygen up to form heavier things, the burning of silicon and so on, producing eventually a core of iron, which then that iron, as it burns, if it ever does fuse, then it will actually produce things that fusion of iron to heavier elements takes away energy, rather than producing and liberating additional energy. And so then you end up with the core is no longer providing the pressure needed to support it, and so then that core will then start to collapse downwards until it reaches the point where the protons and electrons are mostly squished together, making neutrons, and those neutrons can't be squished into each other due to quantum pressure degeneracy, so that you end up with something that kind of repels the additional matter falling onto it, and some of the matter rebounds off, creating a supernova, which we can then see as similar in brightness to some galaxies. And then later on, we can see the supernova remnant, the outer parts expanding out into space. This is an X-ray image from the Chandra X-ray Observatory. So, going on to talk about binary systems. So we know that about 2/3 of all stars are born in numbers of binaries. This is a beautiful interferometric image of the interacting binary algol, which is a case of a star that is a binary in a tight orbit where the one star is actually transferring matter onto the other star. The lower mass, but originally higher mass star here has transferred a bunch of matter onto the other one. You can see it going on. So in cases where, let's say you have a denser star in a binary, typically say a compact object, if you have the two stars get close enough by one means or another, you can actually pull material from the near side of this lower mass star towards, say, a black hole or whatever. Now, you think, okay, well, the two stars are very close, the matter is pulled from the one star, you think it goes straight towards the other star. Well, it does, but since the stars are going around one another, at any given moment as the material leaves the one star heading for the other star moves by the time it gets there. So it misses, and then kind of goes around it, and then will come back and intersect with other material coming. And so then this material will kind of spread out. Some of it will transfer a little bit of angular momentum, and some of it will get a little bit extra angular momentum. The bits that get it move outwards, and the other ones move inwards, and so you have material flowing down onto this dense star. Now the nice thing is if you have a black hole or a neutron star at the core, well, the material that's coming down is losing huge amounts of potential energy as it falls downwards. So it gets moving at extremely high velocities, and when it smacks into anything else, including another little piece of matter, then it raises the temperature up to millions of degrees, and then it can actually radiate X-rays. So we can see this kind of accretion phenomenon all the way across the galaxy and even in other galaxies. So then we have what we call X-ray binaries. And the real thing to remember about these is that the reason why you can generate so much power is not because the neutron star or the black hole is so massive, but rather because it has such a small radius. Right? You can have a star that is the same mass as a neutron star, or even a small mass black hole, which wouldn't generate nearly so much energy from dropping things on it. But because the fact that the neutron star or black hole is so small, let's say you take a neutron star, and say you take a marshmallow out at some distance, and you drop the marshmallow from the distance of the other star down onto the neutron star. When that marshmallow hits the neutron star, it releases about the same amount of energy as a thermonuclear bomb. So it's just because you're accelerating it to such a high speed before it hits. Right? It's getting up to before it hits the surface of a neutron star, it's getting up to something like about 1/3 the speed of light. For a black hole, of course, there's no surface, but the chance is that as it's getting close in, it's going to interact with other things. And you can kind of figure this out that, well, so for a black hole, you know that the escape speed at the event horizon of the black hole is the speed of light, which is why light can't escape. So you have to think, okay, I would just run this film backwards, right? Things that are falling down into the black hole as they reach the event horizon, becoming at close to the speed of light. So take something that's falling down towards the black hole and runs into something else close to it, it's going to be traveling really fast, and it's going to liberate a huge amount of energy. Now, so when you have a black hole and it's accreting, well, it stops accreting and it just stays a black hole. But if you have a neutron star that's accreting from a companion star, well, during the time when it's accreting, it's an X-ray binary, when it's producing huge prodigious amounts of X-rays from the inner accretion disk. But when it stops, then something else can happen. So if you have a neutron star when it's originally born, and then also these neutron stars here that have been an X-ray binary for a while, In either case, the neutron star has a fairly strong magnetic field. It's stronger typically when it's born than later on. But then, at this point, it's been accreting matter for a long time. It's kind of spun up. So it's spinning now very fast. So when neutron stars are born, they might be spinning, I don't know, 30 times a second or so. And after it's been accreting from a companion star, it might be spinning at 300 times a second. Now, these neutron stars have strong magnetic fields. And if you take a strong magnetic field and you change it, any kind of a change in a magnetic field generates a strong electric field. So you have this extremely powerful magnet that's rapidly rotating. That's going to produce a very strong electric field that will accelerate any electrons on the surface of the neutron star. Now, those electrons will then be forced to kind of follow the magnetic field lines because there's a strong force bending them towards whichever direction the magnetic field line is going. And so they're forced to kind of turn as they go, and that acceleration forces them to emit gamma rays. We can see some of those gamma rays. Other of those gamma rays interact with other photons in the area and produce pairs of positrons and electrons. And then those electrons and positrons, then they are accelerated and then they're curving along here. They emit more gamma rays, which then produce more positrons and electrons. So, with huge quantities of electrons and positrons flowing back and forth along these magnetic field lines. And right in the areas over the polar caps, these electrons actually radiate coherently. The details of this we're not quite certain about, but they radiate kind of all together, kind of like a laser, and generate radio emission, which then goes out in this kind of beam. So we can see this kind of beam all the way across the galaxy in some cases as radio emission that sweeps across our line of sight every time the neutron star is pointing in our direction. So if we're over here, then this beam swings over here and then back to us, and we see it once per spin period. So then we call these pulsars, because they appear to pulse, we see the radio flashing at us every time that they spin in our direction. So now let me talk about what we see in the sky, if we look at the optical. So here's the whole sky straight up. This is a combination by Axel Mellinger of the whole sky with the galaxy clearly seen. And it's diffuse emission because there's billions of stars that we can see in a galaxy. And we see the Magellanic Clouds here. But if you then flip it and look in a different wavelength, now looking in X-rays instead of in the optical. And sorry, this is from a previous thing. This is the MAXI all-sky image in the X-rays. So here we can still see the galaxy across here, but now it's like a couple dozen objects are producing the majority of the X-ray emission that we can see, instead of billions making a very diffuse thing. So there's only a small number of objects that are producing most of the strong emission. And those are X-ray binaries. And an interesting thing about them is that a fair number of these bright things we see in the sky are associated with globular clusters. It's the likelihood of seeing a bright X-ray source in a globular cluster compared to the amount of mass in those globular clusters. It's about 100 times more likely to find an X-ray source, one of these X-ray binaries, in a globular cluster than just anywhere, than from the galaxy as a whole. You can put it this way, that 1/10 of all the X-ray binaries in our galaxy are in globular clusters, but only about 1,000 of the galaxy stars are in clusters. So we could ask the question of, how is it that globular clusters produce so many X-ray binaries? And the answer is that they're so dense in the cores. So to step back a second, if you think about the birth of a neutron star as a supernova, this leads, by methods that we're not entirely sure about, causing the neutron star to get what we call a kick. The neutron star gets kind of shoved in one direction. It's traveling at hundreds of kilometers a second. In the majority of cases, say you have a binary consisting of a high mass star and a low mass star orbiting around one another. And the high mass star reaches the end of its life and explodes as a supernova. So now you're left with a neutron star, and that neutron star is traveling at a high velocity. It's going to be unbound from that other star. The two are going to go in their opposite directions. Even if it didn't have a kick, the loss of so much mass in the system would mean that it would probably go off in different directions. So you have to be really lucky to have the kick kind of kick it in just the right way to make the two stars end up going around one another. cluster. So that's kind of rare. So then you're left with most neutron stars left as single. However, in a globular cluster, it's possible to get it a new companion. So here's an example that you have binary stars, two stars going around. Inside a globular cluster, the density is high enough that other stars can interact with these. Say you have another star coming by, they can do this kind of complicated dance and end up exchanging partners. And in this kind of an exchange of partners, the most common scenario is for the lowest mass star to be ejected. So I have here a little movie illustrating this. This is actually a simulation using software designed to illustrate the interaction of stars just by gravity. So that's what's going on here. So I can think of this object here, which is moving along in this direction. Its path is traced out by this line, as a neutron star coming up upon this binary of two other stars. Now, the particular interaction that happens here is not particularly probable, but interactions that are like it can certainly happen and do all the time. And there you go. You finally have the lowest mass star ejected.
What kind of scale and time would that be?
It's a good question. It depends on what the initial binary separation was, but so oftentimes for binaries that are relatively close together in globular clusters, that's an order a day. So you can think of the typical orbits that you could see in there as being the short orbits as being an order a day. So, you know, all that could have happened within about a year or something like that. Any other questions? So that's one method by which you can inject a neutron star into a binary in a globular cluster when it originally was floating around all by itself. So another method by which you can insert a neutron star into a binary is through a direct collision. So the red giants are rather large compared to other stars. They're more likely to get hit by something than anything else. And so if you take a neutron star that slams into a red giant, it can tear off the outer envelope and leave just the core of the red giant, the white dwarf. And then these two will spiral in together as you reject what remains of the envelope, leaving a neutron star and white dwarf together, which can then produce possibly an X-ray binary. And so one of my colleagues at University of Alberta, here's the exact example of the scale of an X-ray binary with an 11-minute orbital period, the white dwarf and the neutron star, and that's the relative size of the Earth. So I have an illustration of a red giant and neutron star smashing together. Actually, the thing that's going around like that is actually the white dwarf that was the core of the red giant. What remains of the envelope of the kind of lower density stuff is around the neutron star at this point. And as these two kind of go around and around, what remains of this gas here is kind of slowing them down and bringing them closer together such that eventually the white dwarf might get close enough to the neutron star to start to transfer mass. So the kind of science that I work on involves a couple different angles. So one of those is trying to understand the details of how X-ray binaries form in globular clusters. And so for that, I look at both trying to understand the kind of nature of specific things that we see in globular clusters and comparing the numbers of different kinds of objects across different clusters. Trying to use neutron star X-ray binaries to try to measure the radius of neutron stars. If we can figure out how large neutron stars are, that can constrain what the interior structure of them is. and to find any black hole X-ray binaries might be in globular clusters. It's been suggested they may exist, but it's not certain yet. So let's go through these. So to start with, globular clusters, of course, come in a range of different characteristics. So these are all Hubble images of, in this case, 47 Tuc, a relatively high-density globular cluster, and the globular cluster M71, which is rather low density. And so if you look at, say, 47 Tuc here, in the optical and in the X-ray, we see obviously many more stars here, and there's a small number of relatively bright X-ray sources. And when I say relatively bright, not nearly as bright as the ones in the picture of the whole galaxy. Those ones are thousands to even a million times as bright as the things we see in here. So to see these objects in a globular cluster requires that we use something like the Chandra X-ray Observatory, which has very, very good angular resolution and very good sensitivity to be able to pick out extremely faint objects. And so there's actually associated with this globular cluster, there's of order 300 different X-ray sources. But of course, there's a few million stars in here. So a lot of these objects in here are due to compact objects that are accreting from another star. Not all of them. Some of them are pairs of normal stars that have enhanced X-ray activity of the kind that our sun has. So how do we identify what these kind of X-ray binaries are? So for example, so here's that same image of, or a similar image of 47 Tuc. With certain objects circled, these are some of the objects that we know now are accreting white dwarfs, or cataclysmic variables. And the reason we know that is because we've been able to identify their companions in the Hubble Space Telescope image. So here's the main sequence and giant branch of 47 Tuc. Over here is the white dwarf sequence. This is all in ultraviolet to blue filters. And so we see a bunch of individual objects along here that are in the aerocircles of these X-ray sources in the X-ray image, which we believe are likely to be cataclysmic variables. So why are they over on this side? Well, that's because there's some contribution to their light from something that's maybe a secondary, that's a star, a donor star, that's maybe on the main sequence, and from the hot white dwarf, and then possibly also some light from the accretion disk, which is also very hot and blue. And so the relative contributions of that mean they'll be somewhere in between here. Maybe the white dwarf, sorry, let me start this way, that maybe the secondary star is relatively large, and so it dominates the light over here. Or in some cases, the secondary star is really tiny, and so the white dwarf is what dominates the light, so they land over here. So we can study these different globular clusters and find out how many different kinds of cataclysmic variables they are, and how they're distributed in period, and how they're produced within the globular cluster, and all this kind of interesting stuff. We can also find them in the radio. So the millisecond radio pulsars that spin hundreds of times a second. We know that these are the progeny of the neutron star X-ray binaries. And there are typically about 10 times as many of these pulsars as there are of the accreting neutron stars in globular clusters. So here in 47 Tuc, we can see a number of them floating around. These things produce the radio emission from these electrons and positrons moving at relativistic speeds. But those electrons and positrons, when they come around and strike the neutron star, well, that's going to kind of heat it up really strongly, up to millions of degrees. And if you had a series, if you had relativistic electrons and positrons hitting you, you would also glow in X-rays. So we can spot these X-rays from the hot surface of these neutron stars. So I mentioned that one of the things I try to do is to try to figure out the structure of neutron stars. So we know some things about neutron stars. We know that in general, they're largely made out of neutrons. So these are given in units of the density of atomic nuclei in general, called rho naught, nuclear saturation density. So there's kind of an outer crust to neutron stars. It's kind of more like normal matter. We think we know what that is. There's an interior, which is mostly neutrons with a few protons and electrons floating around. And then, but when the density gets up to maybe twice that of normal nuclear matter, we're not quite sure what happens. We don't know if at that point it still remains mostly neutrons, or if it's possible then at those points for other kinds of particles to kind of condense out of the soup of quarks that are making up the neutrons. It may be that you produce hyperons or pions or various other things that kind of mix in there with neutrons. Or you could even just kind of dissolve all of the neutrons all together and make a sea of free quarks just kind of wandering around. We're not quite sure what the material that makes up the interiors of neutron stars is. So we don't know for sure then how dense it will be, and therefore we don't know for a given mass of a neutron star what the radius will be. And so that's the kind of thing that we might be able to check, is to actually, if we could measure the radius of some neutron stars, we might be able to figure out just what the interior is made out of. So one thing that we try to do then is to look at neutron stars like this guy here in 47 times, we call X7, and measure the temperature, basically, of that neutron star. And by measuring the temperature and the flux, we can then infer roughly what the radius is. And we end up getting something that looks a little bit weird. This is the contours for this particular object. This is actually the best. That's a typical thing that professors do. They say, well, we'll show you a typical example, and it's actually the very best example. But, so this is the kind of constraints we get. So this is radius versus mass. This region over here is ruled out because anything, if you had a star that actually lay in this region, that would mean that signals would have to propagate through the star faster than the speed of light, which that can't really work. So this is, if we fit this with the data we get from an X-ray telescope with a particular model, we find that it's constrained to lie in this region. And you see this kind of tilts over, right? It's not like we're just measuring the radius, there's some constraint with mass. And the reason is just that if you have a relatively large amount of mass in this object, as we expect for neutron stars, which are 1.5, 2 solar masses, that you're going to bend light and redshift it, and so that will actually alter the spectrum that you get in such a way that if you have a spectrum of an object which is up here, it will look about the same as the spectrum of an object that's down there. So it's an unavoidable degeneracy we have in studying this, is that we're not directly measuring just radius, but some combination of mass and radius. But what we're finding is that typically of order somewhere in the range of 10 to 12 kilometers seems to be kind of the range which these neutron stars seem to be at, which is roughly in accord with what the nuclear physicists think is reasonable from their studies of smashing lead nuclei together and trying to see what that does. So now I want to talk about the black hole X-ray binaries. So black holes in general are rarer and more massive than neutron stars. And up until about 10 years ago or so, it was thought that all the black holes would be ejected out of a cluster. The reasoning goes like this, that the black holes are heavier than the other objects. They're going to sink down towards the center of the globular cluster, and then they're going to interact with each other doing these kind of binary interactions. And then when you make a binary out of two of them, that brings it close together, it kind of releases a bunch of extra potential energy by bringing two black holes together, and so that's going to eject the binary that's newly made in the other star at high velocities from each other. And so they'll all fly out of the globular cluster. And so up until a few years ago, it was thought that all the black holes might be ejected from the cluster and there wouldn't be any black holes left. And in the past few years, there have been several objects found which kind of look like they might be black holes. And so people then went back and did more theoretical calculations, and oh, to their surprise, suddenly they found, oh, actually, we can't just leave lots of black holes in the globular cluster. So that's kind of nice that the theorists eventually turn around and say, well, okay, faced with data that says we're probably wrong, maybe we'll change our minds. So how do we search for these black holes? Well, so one thing we can do is we say, okay, if you look at an X-ray binary, so I showed you the accretion distance, but they also tend to eject, they throw out material at relatively high velocities from very close to the black hole of neutron star. We call it jet. It's blasting out into space. And these jets are moving relativistically and emit synchrotron radiation, which is very strong in the radio. So if we look at the ratio of radio to X-ray flux, it turns out that black holes produce stronger jets at a given accretion rate than neutron stars. So we think, okay, well, if we did a survey in the radio and the X-ray, then we might be able to pick out good candidate black holes. So I'll tell you about one object which we found in the same globular cluster 47Pi, which took us information of the radio, X-ray, ultraviolet, and optical altogether, pieced together. So it's this object here, actually the brightest X-ray source in the globular cluster, which matches with this radio source in this radio image we took recently. and none of the other guys show up. And this guy, the X-ray to radio flux ratio was such as it looked more like a black hole than like a neutron star. So we kept looking at it in more detail and found some really interesting features. So here's an X-ray spectrum, so energy increasing this way and the flux in each energy channel this way. And this is a spectrum in the ultraviolet taken by the Hubble Space Telescope. And what we found in each of these was kind of interesting. There are really strong lines in this X-ray spectrum here due to oxygen. Really, really strong, like so strong we hadn't ever seen anything like that before. And there's a really strong carbon line in the ultraviolet spectrum, but there's no hydrogen or helium lines in the ultraviolet spectrum. And when my graduate student did detailed modeling of this X-ray spectrum, he found that the oxygen lines were so strong that it really couldn't be explained unless the oxygen was making up something like half of all the material flowing down towards the compact object. And, you know, there's strong carbon here, but again, no hydrogen or helium. So then that made us suspect that possibly what we're looking at is a carbon-oxygen white dwarf that's being torn apart by a black hole. And then we found the final clincher. We had been suspecting from the various properties of this X-ray binary that maybe it was in an orbit of about 30 minutes or so. And then when we made what we call a power spectrum, looking for any kind of periodicity, we found this clear signal in a whole bunch of different data sets, right at the exact same period of 28.2 minutes, which we're confident is the orbital period of this binary system. And 28.2 minutes for two things to go around each other is too fast for any normal star to fit into such a short orbit. That has to be a white dwarf. So the point that we come to at the end is to say that we're pretty sure now that this is a white dwarf being torn apart by something that is most likely a black hole. So that was a very nice thing for my PhD student to finish up his PhD thesis with. So I'll stop here apart from questions. We've got these conclusions here about just that the globular clusters high density increase the interaction between stars, and that these make all kinds of things, stellar collisions and X-ray binaries in globular clusters. Okay. Yes?
I've never understood why the rotational axis of a pulsar and the axis of its magnetic field are different.
Yeah, that's a good question. We don't know for sure why it is, but there's no particular reason to expect that the magnetic axis will align with the rotational axis. I mean, you look around and there's very few objects in the world, in the universe which kind of do that. Right? The Earth, certainly its magnetic axis and rotational axis are offset. Virtually all the planets are offset. So there's no particular reason to assume them to be necessarily alike. We don't really know exactly how the strong magnetic fields of neutron stars are generated either. We know where the rotation comes from. If you just simply collapse down the interior of a neutron, of a regular star into a neutron star kind of size, it's going to get something about that size, but spinning very fast. But exactly how the magnetic field is generated is a little bit complicated.
Does the magnetic field wander, or has that been detected on?
That's a good question. There is, it's very hard to measure if the magnetic field is actually kind of tilting with time, but there is one object, the Crab pulsar, for which a few years ago it was measured that actually the magnetic field is actually changing its latitude with time. It's actually tilting, I think, away from the magnetic pole and towards the equator, if I remember correctly. I'm not 100% confident on that. Other questions? Yes?
I thought of this question 3 or 4 times during your lecture, and now I realize the question is asking you to give me another whole lecture. How, in 25 words or less, give me a description of how these globular clusters would look different at different ages.
That's a good question. So,
Like if, for instance, we could find only, 2
so,
billion-year-old clusters, what would be different about them?
So the first thing,
Hertzberg-Russell would be.
So go back to the Hertzberg-Russell diagram, right? So if this is a young cluster instead of one at this age, then the main sequence is going to extend farther over this way. So you're not going to have the giant branch over there. You'll have maybe some giant stars over here and very bright blue stars over here. So then that's going to change the appearance of the cluster. The cluster as a whole is going to get much brighter and much bluer. And so that's basically as you go forward in time, the point at which this curves off moves farther and farther down here.
Less binaries, more binaries?
The overall tendency in a globular cluster is for binaries in general to be reduced over time. However, the binaries that exist tend to be more and more populated with compact objects later in the history of the globular cluster you got. So when the globular cluster is very young, and we do see things that we think kind of look like globular clusters being formed, but we see them only in what we call starburst galaxies. Galaxies where, for instance, you have two galaxies smashing together, and so huge quantities of gas are being crushed down and have shocks through them, and so they produce stars at very high rates. And in some cases, we think these are actually producing things that we would call globular clusters. You can see them easily through all the dust. Maybe the closest example of this is M82, where there are very young clusters are kind of embedded in the dust of that one. It's very hard to see these clusters unless you look at the infrared. Yes.
So I was under the impression that the large black hole will sort of absorb a smaller black hole, and it's a question of mass. Now you're saying that these eject each other instead of joining. Now I would assume then that the ones in the clusters are smaller, and so far don't get the critical mass that's needed to attract and keep the other black hole.
Yeah, that's a good question. So if you have two black holes, and they're just merging around, they're just spiraling around each other, then eventually they'll merge. And in that merger, it's not clear if they kind of get a kick or not. It's been suspected that the gravitational waves actually kind of give them a boost and kind of push them around. But we're not sure exactly how much of it is. But what I'm talking about is if you have an interaction of three black holes. And so if you have three black holes interacting, and you do that kind of dance kind of thing, at the end of it, you end up with two of the black holes coming much closer together than any of the black holes were beforehand. So that ends up releasing a substantial amount of energy. That energy goes into kind of propelling the binary that you've just made away from the third star. So each of them are kind of moving away relatively quickly. The third star is moving faster compared to the other star, but they're all kind of kicked. And so that kind of an interaction could knock all the black holes out of globular clusters. But it depends on exactly how the simulation is run. What we find is that oftentimes you're left with a decent number of black holes still in globular clusters from the simulations we're currently doing. Yes, over here.
Yes, a neutron star radiates thermally, and a black hole radiates Hawking radiation. And I was wondering what portion of the thermal radiation the neutron star could consider Hawking.
So the Hawking radiation from black holes depends to a very high power inversely on the mass of the black hole. So if you have a black hole that's 10 solar masses or so, its Hawking radiation will be very, very, very low in energy and mostly low in frequency of the radio waves. It would be so low that it would be kind of impossible for us to detect it with any current instruments. So even if you take a black hole at 1 solar mass, which would be close to a neutron star kind of mass, it would still generate almost nothing in terms of Hawking radiation. So the Hawking radiation, I think, would only become important for a black hole if that black hole were down at something like, I don't know, the mass of a mountain or less. And then you can actually see it, and as the black hole finally disappears in a final burst of gamma rays, basically, if you take a black hole and it evolves down to the point where it gets to that point, which eventually all black holes should do, eventually they should all disappear due to Hawking radiation. But for black holes of the kind that you find in the centers of galaxies, that might take something like 10 to the 100 power years or so. Right? So quite a long time. So when you get to that point, eventually they will disappear. Eventually they will become a small black hole radiating faster and faster until they disappear and burst to gamma rays. But that, you're not aware that any black holes are close to doing that yet. So for neutron stars, the thermal radiation we're seeing is due to either the initial heat placed in the neutron star by the supernova explosion that created it, or due to material being dropped onto it through accretion in an X-ray binary. And either of those will heat up the neutron star to, say, 1 million degrees or so, whereupon it's radiating X-rays from the surface that we can then observe later on. Yes?
Is there any prospects of seeing these things as eclipsing binaries, or are they too diffuse and too close to really show a signal?
Let's see here. So I particularly love this globular cluster, and so I've pointed out this guy, X7, as a neutron star we can do this work on. This is another neutron star here, called X5, it is numbered in terms of the brightness originally, which would be very good for this, except for the fact that, annoyingly, it's eclipsing. And so we actually see the secondary star, sorry, right there is feedback loop. We actually see the secondary star pass in front of the neutron star and block out its light every 8.466 hours. And in addition to that, we kind of see the accretion disk is kind of blocking some of the light from the neutron star. So it makes it difficult to use this one to do this kind of analysis that we can do with its friend here, who's tilted at some other angle. And actually, let's see here. I believe it is this guy right here is also eclipsing, and that one is every 2.7 hours or so. So we see some of them are eclipsing. You should expect about 20% or so of X-ray binaries to eclipse, and that's roughly in par with what we see. So that's really nice because it gives you the orbital period, and if you know the orbital period, you know something about the density of the donor star, which then can tell you whether it's, say, a white dwarf or something else, which is very helpful.
How good are we at plotting the rest of the velocities in the cluster? Like, we're okay with binary pairs because we can measure the time periods. What's our technology like to measure the velocities of the rest of the cluster?
It's better than you might think, because when you look at Hubble Space Telescope imaging, these Hubble images, the angular resolution there, how far apart you can tell two stars apart from each other is about 1/10 of an arcsecond or so, but you can measure the location of a star more precisely than that, kind of centroid of the star. And so here's the thing, you take two images of a globular cluster like 47 Tuc, or whichever of these, right, that are separated by a few years, you can actually measure the motion of all the stars in the cluster. And so you can see which direction they're all going. And you can use this to study like mass segregation. You can see that the heavier stars kind of tend towards the center of the cluster, and the lighter stars farther out. You can measure the velocities of all the things and see how this is all happening, which is really neat.
Will that give us a lifespan for a globular?
So that's so there's a direction that my mind immediately goes at that. I'm not sure if it's what you're thinking, but I'll go on with it and you can tell me if it's anything like what you're thinking about. So globular clusters do have something we can kind of think of as a lifespan. That the more massive objects kind of segregate down towards the center. And this process is kind of self-sustaining. That the core parts of a globular cluster, is you have stars in there that are moving around. And some are moving a little faster than others. And if you have a few stars interact with one another such that one takes a little bit of extra energy from the others, it gets a boost and is traveling faster than the others, it's going to fly out of the core region. And what's left in the core has less energy. So you can say that the core has kind of knocked something out, and then it kind of sinks down even deeper. So we call this process core collapse. And it leads to the cores of these globular clusters getting denser and denser with time. I think I have another plot in here. The other way. M15. Here we go. So this is an example of a core collapsed globular cluster where you can see the core is really, really dense. Well above, say, 10 to the 6 stars per cubic parsec. And so that's, we see this with the regular stars, and we think the black holes are actually doing this as well. Like earlier and faster, the black holes are kind of self-segregating down to the core. And this is part of kind of the overall lifespan of a globular cluster. They should go through this core collapse. And meanwhile, they're also losing stars from the outside. The lowest mass stars are kind of drifting off into space as they're trying to be ejected out. And so eventually, every globular cluster will kind of dissolve apart. It'll leave maybe some of its densest stars in the core, and everything else will kind of get thrown off into interstellar or intergalactic space. So that will happen, but it will take often quite a long time. Obviously, the globular clusters we see now have lasted for 10 billion years.
So that we can say that M15 might be a more old, an elderly globular?
In the respect of how far it's evolved through the core collapse thing, as opposed to, say, let me go to Omega Sen here, which you see no core in here. This is part of the core of Omega Sen. There's really no dense core here at all. Right? This is a very young cluster in that respect. Although this is not necessarily relevant to the actual physical age of the clusters, which is all fairly similar, but which ones are 10 versus 12 billion years old doesn't matter very much.
If globular clusters eventually throw material off and collapse, do galaxies do the same thing?
Yeah. Although the gravitational potential of a galaxy is much higher than that of a globular cluster. So it's harder for a star to escape a galaxy. They do throw some stars out over time, but I think the time it would take for a galaxy to, I would say, evaporate its stars would be much, much longer than the globular cluster do that. By the time a galaxy were to evaporate a large fraction of its stars, I think at that point you would, almost everything in the galaxy would have turned into a white dwarf or a neutron star or whatever. Yes?
Are all those stars in that cluster or some distant in showing as if they were in the cluster?
Yeah, so the stars that we see here, almost all of these are in the cluster. There's a nice image. Here we go. So looking at 47 Tuc. So 47 Tuc, if any of you have been so lucky as to get down to the southern hemisphere and look around at the night sky, 47 Tuc is one of the nicest globular clusters to look at, but it's declination -72. So it's hard to see. But it is very close to the Small Magellanic Cloud on the sky. It's actually so close that if you take a Hubble Space Telescope image of the central portions of the cluster, you get this where you see the main sequence of 47 Tuc and its giant branch and so on. You see the white dwarf sequence, and there's something else here, which kind of looks kind of like another main sequence, but much lower down because it's farther away. That's actually the Small Magellanic Cloud's main sequence. You kind of the term off around here. So you'll see that in the background. Now, so it's usually when you look at most globular clusters, well, it depends where they are located. If they're located in the plane of the galaxy, then you'll see stars that are both in front of them and behind them along that same line of sight. If they're located out of the plane of the galaxy, then normally you only see stars in front of them because, they could be 20,000 parsecs away or something. So there's hardly any stars behind them, unless it just happens to have a Small Magellanic Cloud.
Any other questions? Okay. Thank you very much. That was, I think that was an example, a typical example of a presentation. As a sign of our appreciation.
Thank you very much.
Thanks, everyone. That is our show for tonight. The meeting